Have you ever wondered what would happen if Isaac Newton, Christian Huygens, James Clerk Maxwell, Albert Einstein and Louis de Broglie sat together for dinner? They'll greet each other in a friendly way and have a nice talk. Quite wrong. They'll fight over the nature of matter. Light behaves like a particle. I passed a beam of white light through two prisms, which were held at such an angle that the light split into a spectrum as it passed through the first prism and was recomposed back into white light by the second prism. Light is made of coloured particles that combine to appear white. That's totally wrong. In my point of view, light consists of waves that vibrate up and down perpendicular to the direction of the wave's propagation. I agree. Through this, my inference is light is a propagating wave of electric and magnetic fields. More generally, coupled electric and magnetic fields travelling as waves at a speed of light. So it's really a wave. Let me show you guys something. If we shine light on a metal of any intensity with energy below the binding energy of an electron, no electrons from the metal will be ejected. As soon as the frequency of light is high enough such that the energy exceeds the binding energy, the electron from the metal can be knocked off the metal. But if light is a wave, it would suggest that as long as we were to wait long enough, light source of any frequency should eventually cause the emission of electrons. See? That's the photoelectric effect. Light can be a particle, so why don't we just accept all? Light can be both a wave and a particle. That's a property only light has. No. You're all behind the times. Matter should have a dual nature. Since light, which is mostly wave, has particle properties, and matter, which is mostly particle, should have wave properties. The wavelength of a matter particle is related to the momentum of the particle. Of course, and my experiment proves this. Electrons behave like waves while they don't look like waves. As the electrons pass through the double slits, we get interference patterns, but this is the nature of waves. Why is this happening? The answer comes through quantum mechanics. When you shoot single electrons through two slits, you get exactly the same interference pattern as you would with light, where you find regions of low and high intensity. The same is found with electrons, where the distribution of each single electron fired ends up becoming a pattern of regions with high and low populations of electrons. The simple explanation for this is the dual nature of matter. Matter behaves as a particle and a wave, so the varying intensity of these electrons is due to the constructive and deconstructive interference from the wave nature of the electron. When we try to detect which slit each single electron goes through, we find that the pattern is no longer created. Let's look at the Mach-Zehnder interferometer. A light beam is first split into two parts by a beam splitter and then recombined by a second beam splitter. Reflection on a beam splitter can cause a quarter wavelength phase shift, and it transmits 50% of light intensity and reflects 50% of light intensity. When we direct light to the first beam splitter, we can observe that all light enters the right detector and none enters the top detector. This is due to interference. Looking at the right detector, in both paths there is one reflection and one transmission in the beam splitter. The two paths have the same phase shift, and we know that in phase waves constructively interfere. Now looking at the paths to the top detector, in the upper path there are two reflections, in the lower path there are no reflections. The upper path has a phase shift of half a wavelength, while the lower path has no phase shift. The waves from the two paths are in antiphase, hence we see destructive interference, so no light enters to the top detector. It's truly a property of waves. When we have a beam of light passing through this setup, we find all the intensity of the light reaches the right detector. We call this the classical case. Now let's consider single photons passing through this setup. So we have reduced the number of photons passing through the setup to one photon detected by the detector per unit time. We find that only the right detector clicks. This can be explained through the fact that when a photon is travelling, it behaves like a wave, but once it's detected at the detector, it acts like a particle and a single click is measured. This is the wave function. The particle lies within the wave function, and it is most likely to be in the region of the highest probability. The highest probability is governed by squaring the wave function. When we square the wave function, we can only get positive values, and this enables us to determine where the particle lies in a region of space governed by the wave function. So hopefully through our discussion of Young's double slit experiment and the Mach-Zehnder interferometer, we are able to share some insight into the nature of light and how it has a dual nature of both particle and wave.